In this video, I will be discussing how to sketch the graph of a rational function. So let the function f be the ratio of two polynomials p of x and q of x, where m and n are the degrees of the polynomials respectively with no common factors, and the polynomial q of x must not be equal to 0. So at this point, let's try to sketch the graph of a given function. So suppose we have here a function f of x which is equal to 1 over x. This function is a rational function, and we will try to sketch the graph of this given function. First, we will find the vertical asymptote of the function. And to find the vertical asymptote of the function, we just set the denominator equal to 0. So in order to find the vertical asymptote, we need to set the denominator equal to 0 and find the value of x that makes the denominator equal to 0. In other words, these are the zeros of the denominator. So as you can see, you have a denominator of x, so x is equal to 0. This is our vertical asymptote, and in other words, our vertical asymptote is the y-axis here. So next is to find the horizontal asymptote. So how do you find the horizontal asymptote of the given function? We can find the horizontal asymptote by just comparing the degrees of the numerator and the denominator. So here, we'll just compare m and n. Now take note that our m is the degree of the polynomial in the numerator, and n is the degree of our polynomial in the denominator. So as you can see that our numerator has a degree 0 and the denominator has a degree 1 in this given function. Since the degree of the numerator is less than the degree of the denominator, it's automatic that our horizontal asymptote is y is equal to 0. In other words, our horizontal asymptote is the x-axis, that is time. So now that we have the vertical asymptote, the horizontal asymptote, we need to plot some additional points near the points of interest in order for you to determine the behavior of the function. Now, take note that we can sketch first the vertical asymptote and the horizontal asymptote in our rectangular plane. So, if you sketch the graph of our vertical asymptote is the y-axis here. So, this is our vertical asymptote. So I'll be using here a dashed line. And also we can sketch the graph of our horizontal asymptote. So our horizontal asymptote is the x-axis. Now take note, asymptotes are not part of the graph. These are lines where the graph is trying to approach more and more closely but will never touch these lines. So we can plot some additional points here so that we will be able to determine the behavior of our graph. So here we have x, and here we have our function f of x, which is equal to 1 over x. Now let's try first when x is equal to negative 5. So when x is equal to negative 5, substituting to the function, our function becomes negative 1/5. So if you plot this point here, we have negative 1, negative 2, negative 3, negative 4, negative 5, and our y there is negative 1/5. So it's here, so it's below the x-axis because it's negative. But if you have a value of our x which is negative 3, the value of the function becomes negative 1/3 if you substitute it here in the denominator. So if your x is negative 3, your y is negative 1/3. So approximately there. If your x is equal to negative 1, the value of the function, if you substitute, it's negative 1 also. So here. But if your x is negative 1/2, so closer to the vertical asymptote, let's try. So if you substitute it here, that becomes negative 2. Because 1 divided by negative 1/2, that is negative 2. So here, when your x is negative 1/2, it's negative 2. But when your x is negative 1/3, so substituting it here, 1 divided by negative 1/3, it's negative 3. So 1/3, it's negative 3, it's here. And if you try negative 1/5, the value of your function becomes negative 5. Because 1 divided by negative 1/5 is negative 5. So it's here, negative 1, negative 2, negative 3, negative 4, negative 5. And if you connect these points, you notice that the graph is a smooth curve that is approaching this y-axis, because this is our vertical asymptote. And as your x goes to negative infinity, your y also is approaching to this x-axis, because our x-axis is our horizontal asymptote. Now, if you substitute the value of your x, which is 0, so when your x is 0, that is 1 divided by 0. Actually, that is undefined. So there is no function at x equals 0, because of course, that is where our vertical asymptote is situated. So there is no function, because remember, a function will never cross the vertical asymptote. So let's continue here, plotting some additional points. So this is our x, and again, this is our f of x, which is equal to 1 over x. So let's try some values closer to our vertical asymptote, but to the right of our vertical asymptote. Say this is 1/5, positive 1/5. Substituting this one here, 1 divided by 1/5 is 5. So if your x is 1/5 somewhere here, your y is 5. 1, 2, 3, 4, 5. So it's here. But if your x is 1/3, substituting it here, 1 divided by 1/3, that is 3. So if your x is 1/3, it's 3. It's here. And if your x is equal to 1/2, substituting it here, 1 over 1/2, it's 2. So if your x is 1/2, it's 2 here. But if it is 1, substituting it here, this is 1 also. So here, 1. And if you try 3, substituting it here, our value of the function becomes 1/3. So if it's 3, 1/3. So when your x is 3, your y is 1/3. And if you try x, which is equal to 5, the value of the function becomes 1/5. So 1, 2, 3, 4, 5, there, it's 1/5. So if you connect these points, you notice that the behavior of the function is approaching to the y-axis, because of course this is our vertical asymptote. And also our function, the graph, is approaching the x-axis, because our x-axis, which is the y equals 0, is our horizontal asymptote. So you see, there is no function at x equals 0, because this is where our vertical asymptote is located. So this is the graph of this function. So as you notice that our graph is approaching the x-axis. As your x approaches to positive infinity, your graph is approaching to the x-axis, above the x-axis. But also, if you have your x to the negative infinity, the graph of the function is approaching also the x-axis, but below the x-axis. And therefore, our x-axis, which is y equals 0, is the horizontal asymptote of this graph. So the function is decreasing indefinitely without bound as x approaches to 0 from the left. And also the function increases indefinitely without bound as x approaches to 0 from the right. So with this information, we can find the domain of the function. So the domain of the function is the set of all x such that x is a real number, so it's just all the real numbers, but x must not be equal to 0. So meaning all real numbers except 0. And also we can find the range of the function. So the range of the function is the set of all y such that y is a real number, but y must not be equal also to 0 because there is no function at y equals 0. So number 2 here is the function f of x, which is equal to 1 over x squared. What is the graph of this function? As you can see that this is a rational function. So of course we need to check if there is a vertical asymptote here. So how do you find the vertical asymptote? We can find the vertical asymptote by setting our polynomial in the denominator to 0. So our denominator is x squared. This is equal to 0. So therefore our vertical asymptote is 0. And this is actually our y-axis. Of course, we will find the horizontal asymptote. So how do you find the horizontal asymptote? We need just to compare the degrees of the numerator and the denominator. So compare m and n. So what is the degree of the polynomial in the numerator? It's in the 0 degree. And also our denominator, the degree is 2. Since the degree of the denominator is greater than the degree of the numerator, our horizontal asymptote is y is equal to 0. In other words, this is our x-axis. So take note, if the degree of the denominator is greater than the degree of the numerator, then automatically x-axis is our horizontal asymptote. Sometimes others, they call it the bottom-heavy function. What do you mean by bottom-heavy? If the degree of the denominator is greater than the degree of the numerator. So that function, it's a bottom-heavy function. So automatically, if the function is bottom-heavy, the x-axis is our horizontal asymptote. So we can now plot initially our graph. So our vertical asymptote is the y-axis. So this is our vertical asymptote. And also our horizontal asymptote is the x-axis. So to determine the behavior of the graph, let us plot some additional points here. So let's have some values of x to be substituted to our function. So if this is your x, then what is our f of x, which is 1 over x squared. So since our vertical asymptote is the y-axis, let's try some values near to this one. Say negative 5. So if you substitute negative 5 here, that is 1 over the negative 5 quantity squared. And that is 1 over 25. So if you plot this point here at x equals negative 5, negative 1, negative 2, negative 3, negative 4, negative 5, our y is almost touching the x-axis here. And if we try x which is equal to negative 3, so substituting it here, 1 over the negative 3 quantity squared, that is 1 over 9. So of course, here, when x equals negative 3, almost at the x-axis, and then if you try say negative 1, it's 1, because 1 divided by negative 1 squared, it's 1 divided by positive 1. And 1 divided by positive 1 is 1. So here, if x is negative 1, it's positive 1. And if you try some value closer to the y-axis, say negative 1/2, substituting it here, 1 divided by the negative 1/2 squared, that is 1 divided by 1/4, and 1 divided by 1/4 is 4. So when your x is negative 1/2, it's 4. So 1, 2, 3, 4 here. And if your x is say negative 1/3, that is 1 divided by negative 1/3 squared, so that is 1 divided by 1 over 9. And 1 divided by 1 over 9 is 9. So at x equals negative 1/3, it's 9. Say, let's approximate somewhere here. So if you connect these points, you notice that you form a graph, a smooth curve like this. So it's approaching the y-axis because of course this is our vertical asymptote. And the graph also is approaching the x-axis because this is our horizontal asymptote. So let's try if x is 0. When x is 0, that is actually undefined. Why? Because division of 0 is not allowed. So there is no function at x equals 0, of course, because this is our vertical asymptote. So let's try some points closer to the y-axis, but to the right of the y-axis, say 1/3. So when your x is 1/3, y divided by 1/3 squared, that is 1 divided by 1 over 9. And 1 divided by 1 over 9, it's 9. So when your x is 1/3, it's 9. So let's approximate somewhere here. But when your x is 1/2, so substituting it here, 1 divided by 1/2 squared, that is 1 over 1/4. And 1 divided by 1/4 is 4. So when your x is 1/2, it's 4. It's here. And when your x, say 1, substituting it here, 1 divided by 1 squared, that is 1 over 1, and 1 over 1 is 1. So it's here. And when your x is 3, we can substitute it here and find that this is 1 over 9. So 1 over 9, because that is 1 over 3 squared. And 3 squared is 9, so that's 1 over 9. So here, that's 1 over 9. So if you connect the points here, you notice that you form a smooth curve that is approaching the y-axis, also approaching the x-axis. So this is now the graph of the function 1 over x squared. So we can find the domain of the function, that the domain of the function is the saddle x, such that x is a real number, but x must not be equal to 0, because there is no function at x equals 0, because this is where our vertical asymptote is located. Also, we can find the range of the function, that the range of the function is the saddle y, such that y is greater than 0 here, and y is also a real number. So meaning, the function is only defined above the x-axis. So y is greater than 0. There is no function below the x-axis. So at this point, let's try another rational function. So suppose we have here f of x, which is equal to x minus 2 divided by x squared plus x minus 6. So what is the graph of this function? Because this is a ratio of two polynomials, we'll try to find out if there's a point of discontinuity in the graph of this function. So here, so to find the points of discontinuity of this function, let us factor out the polynomials. The numerator is linear, so can never be factored anymore, but the denominator can be factored as x plus 3 times x minus 2. And you can check that these are the correct factors of this quadratic polynomial, because x times x, that's x squared. To get the middle term is the sum of the products of the inners and the outers. So 3 times x, that's 3x, and x times negative 2, that is negative 2x. So if you add 3x plus the negative 2x, that's x. And to get this negative 6, that is the product of 3 times negative 2. And you notice that there are some factors that are common to both the numerator and the denominator. So this can be canceled here, and we say that the function can be simplified as 1 over x plus 3. But take note that you must have to add a little condition here, that x must not be equal to 2, because that is the one that we canceled here. So from the factor that we cancel, the x must not be equal to 2, because if x is equal to 2, it makes this factor equal to 0. So this is one value of x that makes the denominator 0. So this is where the function is discontinuous. So if your x is equal to 2, now then we say that if you substitute it here, that is 1 over 2 plus 3, then that is equal to 1/5. Thus, the point is 2 1/5. So this is our hole in the graph. Of course, we need to find next our vertical asymptote. So again, how do you find the vertical asymptote? We can find the vertical asymptote by setting the denominator equal to 0. So equating x plus 3 here to 0, this one, our x is equal to negative 3. So x is equal to negative 3 here is our vertical asymptote. Next is to find the horizontal asymptote. And to find the horizontal asymptote, we just compare the degrees of the numerator to the denominator. Now, looking at this rational function, the degree of our polynomial in the numerator is 1, and the degree of our polynomial in the denominator is 2. So we have a function that is what we call a bottom-heavy function, because the degree of the denominator is greater than the degree of the numerator. So we say here, since the degree of the numerator is less than the degree of the denominator, then our horizontal asymptote is the x-axis here. So we can plot initially our function here. So if this is our point of origin, and this is our 1, 2, and this is our negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, there. And also our y is here 1, 2, 3, 4, 5, 6, 7, 8, 9, there. also here in the negative part of the y. So plotting initially our function, we have here the whole of the graph, which is at 2 1/5. So 2 1/5 is having a hole here, and it has a coordinate of 2 1/5. So we have our vertical asymptote, which is the line x equals -3. So this is our vertical asymptote. So we are using here a dashed line to indicate that this is our asymptote. Also, our horizontal asymptote is y equals 0. So this is our horizontal asymptote. But to have a good picture of our graph is to plot additional points. So let's have some values of x here so that we will be able to determine the behavior of the function. So we have our x and we have our f of x. So when your x is -5, substituting it here, that is -5 minus 2, that is -7. And if you substitute it here in the denominator, that is -5 squared, which is 25. So 25 plus the -5, so that is 20. And 20 minus 6, that is 14. So -7 over 14, it's -1/2. So if you plot it here, -1, -2, -3, -4, -5, but it's -1/2. So it's here. Now let's try some value of x, say -4. So substituting it there, -4 minus 2, that is -6. So substituting -4 in the denominator, we have -4 squared, which is 16. And 16 plus the -4, it's 12. And 12 minus 6 is 6. So 6 divided by -6 is -1. So when your x is -4, -1, -2, -3, -4, it's -1. So it's here. So let's try when x is -3. So our numerator is -3 minus 2, it's -5. But if you substitute in the denominator, -3 squared, it's 9. 9 plus the -3 is 6. And 6 minus 6 is 0. So therefore, this is undefined when x is equal to -3. So there is no function at x equals -3 because of course, this is where our vertical asymptote is located. So let's try some value closer to x equals -3, but to the left of this -3, so say this is -3.5. So substituting our x here to the reduced form of our function, because anyway our x is not 2, because 2 is where our whole is located, then it's okay to substitute our x. So 1 over -3.5 plus 3, that is 1 over -0.5. And 1 divided by -0.5, that is -2. So when your x is -3.5, the y value is -2. So it's here. And if you connect this point, you notice that you form a curve that is approaching this vertical line, x equals -3, and it's approaching also to the x-axis, because our x-axis is our horizontal asymptote and x equals -3 is our vertical asymptote. So let's try some values of x that is closer to x equals -3, but from the right of it, say -2.5. So 1 over -2.5 plus 3, that is 0.5. So 1 divided by 0.5, that is 2. So here, -1, -2, -2.5, it's 2. 1, 2. It's here. So let's try negative 2. When x is equal to negative 2 plus 3, that is 1. So the value of y is 1. So it's here. When your x is negative 2, the value of y is 1. And when that is negative 1, so when your x is negative 1, 1 over the negative 1 plus 3, that is 1/2. So negative 1, the y is 1/2. And when your x is 0, so 1 over 0 plus 3, that is 1/3. So here it's 1/3. And if you connect these points, you notice that you form a smooth curve that is approaching this vertical line. X is equal to negative 3, but also it is approaching to the x-axis at x going to positive infinity, because our x-axis is our horizontal asymptote. But take note that our graph is hollow at this point. So this is the break of the graph. This is the point of discontinuity of the graph. So how do we find the domain of the function? The domain of the function is the set of all x such that x is a real number, but x must not be equal to the negative 3, and also x must not be equal to 2, because this is where the function is not defined. It's not defined at x equals negative 3 because this is where our vertical asymptote is located. And the function is not defined at x equals 2 because it is a hole in this graph. This is a point of discontinuity of the graph. But what is our range of the function? Our range is the set of all y such that y is also a real number, and y must not be equal to 0, and also y must not be equal to 1/5. Why? Because at y equals 0, this is our horizontal asymptote. And y at 1/5 is also not defined because this is where the whole of the graph is located. So at this point, it's time to present to you the guidelines for sketching the graph of a rational function. So let the function f of x be the ratio of two polynomials, p of x and q of x, where m and n are the degrees of the polynomials p of x and q of x, respectively. So our m is the degree of the polynomial in the numerator, and n is the degree of our polynomial in the denominator, where no common factor is found. And the polynomial in the denominator must not be equal to 0. So first, in sketching the graph of a rational function, it's good to determine first the points of discontinuity if there's a point of discontinuity in the graph. If there's a point of discontinuity in the function. Number 2, find and plot the y-intercept if there's a y-intercept by evaluating the function at x equals 0. Because at the y-intercept, the x must be 0. So evaluating the function at x equals 0 is our y-intercept. Third, the x-intercepts, if there's any, can be found by setting our numerator equal to 0. Because at the x-intercept, the y must be 0. So if this is 0, 0 times the denominator is 0. So actually, setting the numerator equal to 0 is what we call the zeros of the numerator. And the zeros of the numerator is our x-intercepts. Number 4, plot the vertical asymptotes using dashed lines by determining the zeros of the denominator. So the vertical asymptotes can be found when you set the denominator equal to 0, because when this is 0, it makes the function undefined. It is because at the vertical asymptote, the function is not defined. So to find the vertical asymptote, set the denominator equal to 0. And the zeros of this denominator are the vertical asymptotes of the function. Number 5, the graph of the function f has at most one horizontal asymptote by just comparing the degree of the numerator and the degree of the denominator. So if the degree of the numerator is less than the degree of the denominator, so it's here, if your m is less than n, which means that the function is bottom heavy, the graph will have a horizontal asymptote y equals 0, or the x-axis. So there's no need for you to compute, but just notice that if the function is bottom heavy, the x-axis is our horizontal asymptote. But if the degree of the numerator is equal to the degree of the denominator, then the graph of the function f will have a horizontal asymptote y equals the leading coefficient of the numerator divided by the leading coefficient in the denominator. So a is the leading coefficient of the polynomial function p of x, and b is the leading coefficient of the polynomial function q of x. But if your degree of the numerator is greater than the degree of the denominator, so if the degree of the numerator is greater than the degree of the denominator, then the graph of the function f has no horizontal asymptote. Number 6, if the degree of the numerator is greater than the degree of our denominator and it is 1 degree higher, in other words, if the degree of the numerator is 1 degree higher than the degree of the denominator, then the graph has an oblique asymptote. No horizontal asymptote, but it has an oblique asymptote. And the oblique asymptote can be found by dividing the polynomial in the numerator by the polynomial in the denominator. And the quotient is h of x plus r of x over q of x, where the r of x is the remainder when you divide the polynomial in the numerator by the polynomial in the denominator. And the quotient is our oblique asymptote. So y is equal to h of x. So whatever is the quotient will be equated to y, and y is equal to h of x is our oblique asymptote of the graph. So take note, if the degree of the numerator is greater than the degree of the denominator, no horizontal asymptote. But if the degree of the numerator is 1 degree higher than the degree of the denominator, then you will have an oblique asymptote, which can be found by dividing the polynomial in the numerator by the polynomial in the denominator, and the quotient will be our oblique asymptote minus the remainder. So just drop the remainder, just the quotient is our oblique asymptote. So there's an oblique, no horizontal. But if the degree of the numerator is greater than the degree of the denominator, but it is not 1 degree higher, but it is more than 1 degree higher, then there is no horizontal asymptote, there is also no oblique asymptote. And to determine the behavior of the graph of the rational function, you may plot some additional points near to the points of interest. What are these points of interest? The X-intercepts, the Y-intercepts, at the vertical asymptotes, at the horizontal asymptotes, in order for you to observe the behavior of the graph of a rational function. So number 1, determine the points of discontinuity, if there's any. Number 2, determine the Y-intercept by evaluating the function at x equals 0. And next is to find the X-intercepts by setting the numerator equal to 0. And to find the vertical asymptote, set the denominator equal to 0. Because the zeros of the denominator is where we can find our vertical asymptotes. And then you can find the horizontal asymptotes by comparing the degree of the numerator by the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then you will have the x-axis as your horizontal asymptote. This is popularly known as the bottom-heavy function. So if the function is bottom-heavy, automatically the x-axis is the horizontal asymptote. But if the degree of the numerator is equal to the degree of the denominator, our horizontal asymptote can be found by the leading coefficient of the numerator divided by the leading coefficient of the denominator, and set that quotient to y. So this is the equation of our horizontal asymptote. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Maybe it has an oblique asymptote. And how do you know that there is an oblique asymptote? There is an oblique asymptote if the degree of the numerator is 1 degree higher than the degree of the denominator. And to give you a full grasp of the behavior of the function, you need also to plot some additional points near these points of interest. The points of discontinuity, the y-intercept, the x-intercepts, the vertical asymptotes, the horizontal asymptote, if there's any, and the oblique asymptote, if there's any. Now, let's proceed to number 4 here. So, what is the graph of the rational function f of x, which is equal to x over x squared minus x minus 6 plus 2. Now, remember our guidelines in sketching the graph of a rational function, that we must first find the points of discontinuity, if there's any, in a given rational function. And to find the points of discontinuity is to look for the common factors between the numerator and the denominator. And combining this whole number with this fraction, and you know this whole number is understood to have a denominator of 1, we have the LCD of x squared minus x minus 6 here. So x squared minus x minus 6 divided by this 1 is 1 times x, so we have x there. So x squared minus x minus 6 divided by 1 is this quadratic polynomial, and multiplied by 2. So we have here 2 times x squared minus x minus 6 here. And simplifying, we have, if you distribute this 2 with this trinomial, so 2 times x squared, we have 2x squared. And 2 times negative x, it's negative 2x, and plus x, we have minus x. And 2 times negative 6, we have negative 12. And we just copy the denominator x squared minus x minus 6 there. Since there is no common factor between the numerator and the denominator, then therefore there is no point of discontinuity except for the vertical asymptote. So let's start here, the y-intercept. So how do you find the y-intercept of a function? We just evaluate the function at x equals 0 here. So if your x is 0, we just substitute it there. So that is 0 over the denominator of 0 squared minus 0 minus 6 plus 2. And remember that this 0 divided by negative 6, because this 0 squared minus 0 is just 0, and 0 divided by negative 6 is 0 plus 2, that is 2. So the y-intercept here, it's 0, 2. And this is our y-intercept of this graph. And why is it I wrote here 0 in the x-coordinate? Because at the y-intercept, the x-coordinate must be 0. So let's find next the x-intercept of the graph, if there's any. So how do you find the x-intercept? You just set the numerator equal to 0 here. So our numerator, looking at this simplified form of this function, we have the numerator of 2x squared minus x minus 12, and this is equated to 0. To find the x-intercept. Remember the x-intercept, the y-coordinate must be 0. And why do we set the numerator to 0? Because your y, which is the f of x, must be set to 0. So 0 times the denominator is 0. So 0 equals the numerator. So that's why we set the numerator equal to 0. So this one, we find it difficult to do the factoring, so we'll use the quadratic formula in finding the roots of this quadratic trinomial. So we have our a, which is 2, and we have our b, which is negative 1, and we have our c, which is negative 12. And finding the roots of this quadratic trinomial, we have x, which is equal to the negative b, and the negative of the negative 1 is 1, plus and minus the square root of your b squared, and the square of negative 1 is 1, minus 4ac. Our a is 2, and our c is negative 12. There. And this is divided by 2 times a, and our a is 2 here. So what is our x? Our x is 1 plus and minus the square root of 1, and 4 times 2 is 8, and 8 times the negative 12 is negative 96. So minus the negative 96 is plus 96 there, and this is divided by 4. So our x here is equal to 1 plus and minus the square root of 97 all over 4. So our x's here is x is equal to 1 minus the square root of 97 divided by 4. And using your calculator, approximately our x is equal to negative 2.212 here. And the other x is equal to 1 plus the square root of 97 divided by 4. And using your calculator, that is 2.712. Then therefore, the x-intercepts are the points negative 2.212, and the y-coordinate is 0. Also, we have 2.712, and the y-coordinate is also 0 because this is an x-intercept. So these are the 2 points that are called the x-intercepts of the graph. Now, let's proceed to the next step, which is finding the vertical asymptote of the function. And to find the vertical asymptote is to set our denominator equal to 0 here. So setting this denominator equal to 0, we have x squared minus x minus 6 is equal to 0. And we can easily factor this quadratic trinomial as x minus 3 times x plus 2 here. And you can check that x times x is x squared. And to get the middle term of negative x, it is just the sum of the products of the inners and the outers. So negative 3 times x, that is negative 3x, and x times 2, that is positive 2x, and if you add negative 3x plus 2x, it's negative x. And negative 3 times 2, that's negative 6. And that is our third term. So setting its factor to 0, so x minus 3, which is equal to 0, and the other one, x plus 2, which is equal to 0, our x's here is equal to 3 and negative 2. So therefore, these are our vertical asymptotes. X equals 3 and x equals negative 2. Now at this time, let's find also the horizontal asymptote. So How do you find the horizontal asymptote here? You just compare the degree of the numerator and the degree of the denominator. And since the degree of the numerator is 2 and the degree of the denominator is 2, then the degrees are equal. So we say here, since m is equal to n, our m is the degree of the numerator and our n is the degree of the denominator, then because they are equal, our horizontal asymptote is just the leading coefficient of the numerator in the polynomial in the numerator, which is 2 here, and divided by the leading coefficient of the polynomial in the denominator, which is in this case 1. So this is 2 over 1, or in other words, we have y equals 2. So this is our horizontal asymptote. So we can initially plot our rational function here, and remember, by plotting our points of interest. So first, our y-intercept is 0, 2, so 1, 2, it's here. So this is our y-intercept 0, 2, and we have our x-intercept, which is negative 2.212, so 1, 2.2 here. And also we have 2.7, 1, 2.7. Those are our x-intercepts. And we have also our vertical asymptotes, which is x equals 3. So here, this is our vertical asymptote, x equals 3. It's a vertical line, 3 units from the y-axis. And we have another vertical asymptote, which is at x equals negative 2. So we have it here, which is 2 units to the left of the y-axis. There. And then we have also the horizontal asymptote, which is equal to 2. So here is our horizontal asymptote. But we don't know where is the graph in this drawing. So first, let us plot some additional points so that we would know the behavior of the function. So plotting near the point of interest, we have our x, and our function is at the point x over x squared minus x minus 6 plus 2. This is our function. So when your x is equal to 2, substituting it there, so that is 2 over 2 squared, which is 4, minus 2, which is now 2, and 2 minus 6, it's negative 4. So this is negative 4 plus 2. So that is 2 minus 1/2. And 2 minus 1/2, it's 1 and 1/2, or 3/2. So here, when your x is 2, that's 1 and 1/2. Now, we can connect this one. We understand that this is moving downward here, and it connects here like that. But I'm not sure if it's going upward or if going downward. So let's try when x is equal to negative 1. So substituting to the numerator, negative 1 over negative 1 squared, which is 1, minus the negative 1, so that is plus 1. So 1 plus 1 equals 2, and 2 minus 6 equals negative 4. So negative divided by negative, it's positive. So this is positive 1/4 here. And if this will be added to 2, this is equal to 2 and 1/4, or this is 2.25. So if x is negative 1, that's 2 and 1/4, it's here. So it's above this horizontal asymptote. So if you connect, the graph is like that. It's approaching, it's rising indefinitely without bound, but approaching this vertical line because this is our vertical asymptote. And I'm sure that the graph of this is moving downward because this is our vertical asymptote. So it's impossible to go up there because it will cross this horizontal asymptote. So I'm sure it will also approach this horizontal asymptote there. Or you can check when your x is negative 3. So the numerator is negative 3 over negative 3 squared, which is 9. 9 minus the negative 3, that is plus 3. So 9 plus 3, it's 12. And 12 minus 6, it's 6. So this is negative 1/2 plus 2. So 2 minus 1/2, that is 3/2. So at x equals negative 3, that's 3/2. So it's here. So we're sure that it's below this horizontal line because this line is 2 units above the x-axis. So this is 1 and 1/2. Now let's also plot at this point to the right of this vertical asymptote. So let's try maybe 4. So substituting 4 there, so 4 over 4 squared, which is 16, and 16 minus 4, it's 12, and 12 minus 6 is 6. So this is 2/3 added to 2, that is equal to 2 and 2/3 here. So when your x is 4, 1, 2, 3, 4, that's 2 and 2/3, 1, 2, and 2/3. So we're sure at this point that the graph is above this horizontal asymptote. So it's approaching this vertical line because this is the vertical asymptote, and approaching this horizontal line y equals 2 because this is our horizontal asymptote. Then therefore we can determine the domain of the function, that the domain of the function is the settable x, where x is a real number. So it's defined in all the real numbers except these points, negative 2 and 3. So x must not be equal to negative 2 and x must not be equal to 3. So the function is defined in all x's except from these two vertical asymptotes, which is x equals 3 and x equals negative 2. So what is the range of the function? The range of the function is the settable y such that y is a real number. Why? Because the function is defined in all y's, and there is no point of discontinuity except for these vertical asymptotes. So let's proceed to example number 5. What is the graph of the rational function f of x, which is equal to x squared minus 3x minus 4 divided by x squared minus 2x minus 8 here? So first, let's find out any points of discontinuity of this function. And to find the points of discontinuity of the function is to look for the common factors between the numerator and the denominator. And we can factor this one as x minus 4 times x plus 1. And you can check that x times x, that's x squared. And to get the middle term, it is the sum of the products of the inners and the outers. So negative 4 times x, that is negative 4x, and x times 1, it's x. So adding them, x plus the negative 4x, that is negative 3x, and negative 4 times 1, that is negative 4. Also, we can factor the denominator as x minus 4 times x plus 2 here. And you can check that x times x, that's x squared. And to get the middle term of negative 2x, we just multiply the inners, negative 4 times x, negative 4x. And we multiply the outers, x times 2, that is 2x. Adding them, negative 4x plus 2x, that is negative 2x. And negative 4 times 2, that is negative 8. So these are the correct factors of this quadratic polynomial. And you see that there is a common factor between the two, which is this x minus 4. So you can cancel these two. So the reduced form of this function is x plus 1 over x plus 2. But there is a point of discontinuity that we canceled this factor, and that is when x is equal to 4. So here, the function must not be having x that is equal to 4. The point of discontinuity occurs when x is equal to 4. So if your x is equal to 4, then if you want to find the y, even though that point is not in the graph, so substituting it here, that is 4 plus 1 all over 4 plus 2. So this is equal to 5, 6. Then therefore, the point of discontinuity is this, 4, 5, 6. So this is our hole in the graph. So next is to find the y-intercept, if there's any, in this rational function. So how do you get the y-intercept again? The y-intercept is obtained by evaluating the function at x equals 0, because at the y-intercept, the x is 0. So what is f of 0? We just substitute it here, and that is 0 squared minus 3 times 0 minus 4. And in the denominator here, we have 0 squared minus 2 times 0 minus 8. And if you do the simple arithmetic, so these zeros goes away, what will remain is negative 4 over the negative 8. And the negative divided by negative, that's positive. So this is positive 1/2. If you reduce 4, 8. So our y-intercept occurs at 0, 1/2. So this is now our y-intercept. Now remember that in a function there must be at most one y-intercept. Now let's proceed to our x-intercept. Our x-intercept can be obtained, remember, from our guidelines, can be obtained by setting the polynomial in the numerator to 0. And why is that? Because at the x-intercept, the y must be 0. So if your y is 0, so your f of x is 0, and this one times the denominator, that's 0. So what will remain is the numerator. So setting the numerator to 0 is our x-intercept. Using this reduced form, the numerator is x plus 1, and we set that one to 0. So therefore, x is equal to negative 1. So what is our x-intercept? Our x-intercept is negative 1, 0. And why do I have 0 in the y-coordinate? Because at the x-intercept, the y must be 0. So this is our x-intercept, only one x-intercept. So let's proceed also our vertical asymptote. Our vertical asymptote can be obtained by setting the denominator equal to 0. And our denominator there is x plus 2. So x plus 2 is equal to 0. Therefore, x is equal to negative 2. So this is again our vertical asymptote. Now let's proceed also to our horizontal asymptote. Our horizontal asymptote can be obtained by comparing the degree of the numerator to the degree of the denominator. And looking to the degree of the numerator and the degree of the denominator, they are just equal, because the degree of the numerator is 2 and the degree of the denominator is also 2. Then therefore, our horizontal asymptote is the quotient of the leading coefficients of the polynomial in the numerator divided by the leading coefficient of the polynomial in the denominator. So we have 1 over 1, because the coefficient here is understood to have a 1, and in the denominator the leading coefficient is still understood to have a coefficient of 1. So our horizontal asymptote is y equals 1. So this is our horizontal asymptote. So at this point, we can initially sketch the graph of our rational function here. So plotting our point of discontinuity here, which is at 4, 5, 6, 1, 2, 3, 4, 5, 6, which is almost to 1, so it's here, and it has coordinates of 4, 5, 6. And we have also the y-intercept, which is at the point 0, 1 half. 0, 1 half is here. And then we have also our x-intercept, which is at the point negative 1, 0. So it's here. Negative 1, 0. And also we have our vertical asymptote, which is x is equal to negative 2. So our vertical asymptote is here. X is equal to negative 2. And we have also our horizontal asymptote at 1. So in order for us to have a good picture of the behavior of the function, let's plot some additional points here. So if this is your x, so our function is x plus 1 over x plus 2, where your x must not be equal to 4. So here I want to see what is the behavior of the function at x equals to 3, near at the point of discontinuity. So when your x is equal to 3, 3 plus 1 is 4, and 3 plus 2 equals 5, so that is 4/5. So that is almost to 1, so it's here. Then I'm sure that if you connect this one, you form a graph like this, a smooth curve like this. So the graph is approaching this horizontal line y equals 1, because this is our horizontal asymptote, and it is also approaching this vertical line downward, because this is our vertical asymptote. But I don't know at the left of this vertical line whether the graph is up here or down here. So let's try some values to the left of this vertical line, x equals negative 2. So let's try, say, negative 3. Where is the function at negative 3? So substituting negative 3 here, negative 3 plus 1, that is negative 2. And negative 3 plus 2, that is negative 1. So negative divided by negative, it's positive. So when your x is negative 3, your y is 2. 1, 2. So it's here. And let's try one more. Example, negative 4. So negative 4 plus 1, that is negative 3. Over negative 4 plus 2, that is negative 2. And negative divided by negative, it's positive 3 halves here. And 3 halves is 1 and 1 half. So that is 1 and 1 half, or 1.5. So where is that? 1, negative 1, negative 2, negative 3, negative 4. But the y is 1 and 1 half. So it's here. And let's try one more. Example, negative 5. Negative 5 plus 1, that is negative 4. Negative 5 plus 2, that is negative 3. And negative divided by negative, it's positive. So this is 1 and 1/3. So 1 and 1/3 somewhere here. So that's why we're sure that this graph is approaching that horizontal line and approaching also this vertical line. So this is the graph of the function, and we can determine easily the domain of the function. That the domain of the function is the set of all x such that x is a real number, but x cannot be equal to -2 because it is where we find our vertical asymptote. And also the function is not defined at x equals 4. So x must not be equal to 4 because it's a hole in the graph. So the function is not defined at that point. So what is the range of the function? The range of the function is the set of all y such that y is a real number and y cannot be equal to 1 because it is where we can find our horizontal asymptote. And also y cannot be equal to 5, 6 because it is where we find our point of discontinuity in this function. So this is the hole in the graph, therefore the function doesn't exist at that point. So y cannot be equal to 5/6. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.